What I attempted to do in that first zero lesson video that you saw, 0.1, is describe to you the parent function sine and cosine. Now we're going to deal with some of the transformations of sine and cosine functions. They have several characteristics here that I would think it would be wise for you to pay some attention to about the domains and the ranges, which are both the same for sine and cosine functions. The domains mean that we can wrap around in either direction in infinite number of times. The ranges, the highest values that sine and cosine values can ever get are -1 and +1 as parent functions. You see some minor changes in the x-intercepts, y-intercepts. Continuity is the same everywhere. Symmetry, that's awful nice to know your symmetry on the origin. The symmetry about the origin means you can rotate 180 degrees. If it's an even, as we have here, it's a y-axis, so you can see the cosine function, you could flip it about the y-axis, it's an even function. Extrema, they're talking about the high points and low points for the maximum minimums. So you have maximum points at +1, -1. They're happening at different locations, and they have the description of where those are happening. That's not the biggest fish to fry there, but they give some information on that. The end behavior is unlimited. There's no limit to either of these as we approach the end because they keep cycling through their values between -1 and 1 throughout their entire graph. And the oscillation, whenever they say oscillation, just says what's the range of the outputs, and they go from a -1 to 1 inclusive. So what we're going to look at is we're going to look at transforming some of these sinusoidal curves. The first thing we're going to do is we're going to talk about transforming them by changing the amplitude. The amplitude of this function is going to change the height of it. Just to back up just a bit, they give us two different equations here. These are sinusoidal because they're sine-like. Any variation of the sine curve is called a sinusoidal curve. So these are the variations that we're going to make to them. We're going to do a vertical stretch. We're going to do a vertical translation. Notice the multiplication always represents some type of a stretch. Any addition subtraction is going to end up representing a slide up and down or left and right. So we've got a vertical stretch with multiplication of a. We've got a vertical stretch out, or vertical translation. If we go back to some fundamental ideas, if we had a function y equals f at x, then if we took y equals some constant a times f at x, that's a vertical stretch, so we're going to stretch things vertically. If we had y equals f at x plus d, that's going to move it up and down. It's a translation, so anytime we add and subtract. We also have some that were y equals, if we have f times a, I'm just going to use the b, I'll stick with the letters I have there, b times x. Now, anytime it's inside the grouping symbols, we're acting on the input value first before the function takes any value of it. This is going to be a horizontal. So we're going to look at horizontal transformations. Anytime we multiply, it's got to be a stretch or shrink. So b, multiplying inside the parentheses, is going to be a horizontal stretch or shrink. And then we can also act inside the parentheses. And I'll leave the b out and put plus c. Since we're adding inside the parentheses, we're going to look at horizontal translation. So inside the parentheses are horizontal transformations. So we've got a stretch shrink, slide left or right. Outside the grouping symbols or outside the input, if we're going to add something on, it's always a translation. But if it's outside the parentheses, up, down. If it's inside, it's left, right. And these, if you remember, are always kind of counterintuitive. If we add c, it really moves it to the left. If we subtract c, it moves it to the right. If we multiply by a number that's bigger than 1, it really shrinks it. If we multiply it by a number smaller than 1, it stretches it. And then over here, we're looking at multiplying by a outside the parentheses. It'll be our vertical stretch. Okay, the third panel. So, okay, that's the first part that we're going to work on, these vertical stretch and shrinks. We're going to move them and change their amplitude. Now, this has a special name anytime it's a vertical stretch or shrink in sine and cosine graphs. It's called an amplitude change. So here's the first one. I'm going to enlarge the graph I have here. I was hoping that those would be invisible in behind, but that's okay. So we're going to get some more practice of graphing these curves, their parent functions, and then the change, the transform function. So describe how the graphs of f at x and g of x are related, then find the amplitude of g of x, and sketch the two periods, both functions on the same coordinate axis. So if you look at this, this is our parent function. The only thing that we have changed is we multiplied it by a constant in front. That should be a vertical shrink. So The comparison between f of x and g of x is going to be 1/3 the height of the cosine of x. So find the amplitude of g of x? The amp of g of x is 1/3. Next thing we're going to do is we're going to sketch the graphs on 2 periods. So what I'm thinking of whenever I graph these is that unit circle in the ordered pair, 1, 0, 0, 1, -1, 0, and 0, -1. I know on cosines I want to grab the x value, so at 0 it's 1. At pi halves it's 0. Oops. I said it right and wrapped it wrong. At 0 radians it's 1. At pi halves it's 0. At pi it's a -1. At 3 pi halves we're back to 0. And then once we get fully around 1 rotation, we're at 2 pi, we're back to 1. And they're going to repeat those values. So if you remember from last year, cosines are max and min starters. So they should start at a maximum, go down to minimum, back up, and it's going to keep repeating that cycle of values. So that is our parent function. This is f of x. And then we're going to graph the other function, 1/3 cosine of x. Now the only thing this is going to do is it's going to take all the values that we just graphed and it's going to take 1/3 of them. So 1/3 of 1 is 1/3. A third of 0 is still 0. A third of a -1 is 1/3, -1/3. A third of 0 is still 0. We take a third of a positive 1 is a positive third. And a third of 0 is still 0. And then a third of a -1 is a -1/3. A third of 0 is 0. And a third of 1 is 1/3. So that vertical transformation, that vertical shrink that we just had, took 1/3 of all of your outputs. Now whenever you take a third or any amplitude change of zeros, the zeros are never changed in any amplitude variation. All that we're going to do is we're going to take every other output and change them to 1/3 the side in this case. So it's a vertical shrink in this case, just as we would think. Anytime you multiply by a number between 0 and 1, it's going to shrink your graph vertically. So that's the first thing that we wanted to do, and we're finished with it. So we'll clear and we'll start another one. In the second one, it's a sine curve, so we're going to get some practice graphing the parent function of a sine of x, and then we're going to graph 5 sine of x. The first thing that we should be able to quickly recognize is the period of this function, the amplitude of this function. The amplitude is simply the multiplier that we're multiplying times sine. So the amplitude for this function, g of x, has an amplitude of 5, which means all of the sine values of this function are going to get multiplied by 5, so this is going to represent a vertical stretch. Okay, so again, getting this reference so that I get my order pair sitting in front of me. It's the order pair 1, 0, 0, 1, -1, 0, and 0, -1. Now on a sine curve, the sine curve always grabs your y values. So the first thing it's going to do is the sine of 0 is 0. So if you remember, sines are centerline starters. At quarter of a turn or pi halves, we're at our maximum value of 1. And then we're back at 0 by the time we're at pi. At 3 pi halves, we're at -1, which is down here. And by the time we rotate around once, we're back to our start. And then these values will cycle through again. We'll be at 1, 0, -1, 0. So here's the pattern of our sine curve with an amplitude of 1. This is our parent function. And this would continue on as indefinitely as we want to go in either direction. Now what's different in this one is we change the amplitude, and that amplitude is a vertical stretch of 5 times. Now when you multiply zeros times 5, it doesn't change it, but a 1 times 5, then the maximum value is going to come up here to a positive 5. Zeros remain unchanged. The -1 becomes a -5 because we're going to multiply it by -5. 0, positive 5, 0, -5, back to 0. So here's what an amplitude does to our graph. It changes the peaks and valleys of our graph, the maximum minimums. It leaves the zeros unchanged, and we have our second graph sketched. Okay. And then we'll go to our final graph here as an example. Whoop, that's not what I wanted. Let's try it again and again. Just want to shrink that down. And I'm going to graph the cosine of x. I'm going to take this a little bit quicker this time. Cosines harvest the x values, so when we're graphing our parent function, y equals cosine of x. Remember, cosines are maximum and minimum starters. The cosine of x is a cosine of 0 is at its maximum value of 1. A pi halves at 0. Pi is at negative 1. 3 pi halves is 0. 2 pi is 1. We repeat the cycle of values for 2 periods. Cosines start at a maximum or a minimum. In this case, we've seen 2 maximum starters. Sines are centerline starters. The only thing different about this one, we're going to do a vertical stretch of 2 times the height. So all the non-zero values get doubled. Even though the zeros are getting doubled, they remain unchanged. So it cannot change the zeros. It can only change the location of your non-zero points. So we're going to see a curve that looks just like the cosine curve, only it's a vertical stretch. So amplitude change, same thing as a vertical stretch. We saw it in the unit 1.5. We're just applying it to these particular functions. So hopefully that goes pretty smoothly for you.